Good morning, guys. We're starting chapter 2 here, finally getting into a little bit of calculus. Chapter 2, limits and continuity. Before we really kind of start, I guess kind of the question is what the heck is a limit? Well, we're going to cover some of that in here, but let's say we had a function f of x that equaled x squared, okay? Well, what a limit is a limit is a value that the function is approaching. As they get closer and closer to an x value, what is the y value that's coming out? So if I wanted to know what is the limit as x approaches 3 for this function f of x equals x squared, oh, I can see the limit is going to be 9 because y is going to be approaching 9. Okay, another function. It's a really boring function. Polynomials are really super boring functions. Well, how about if I had a rational function f of x equaled 5 over x minus 2, and I had a graph of that, okay? Well, what the heck? What is the limit as x approaches 2? And everybody's going to look in here and they're going to say, whoa, whoa, x can't approach 2. When they're looking at that, they're like, oh, I see what you did back here, Kruger. You just plugged 3 in there and it spit out a 9, so you said the limit was 9. Well, over here, I'm spitting in 2, and what happens is I get 5 over 0, I get undefined, okay? But what's the limit? Okay, well, I can look at, I guess it matters which side of 2 I'm approaching on. So if I'm looking on the right side of 2, I can see that the y value is going to infinity. And if I look at the left of 2, okay, so this would be my right side of 2. If I was looking at the left side of 2, I can see y is approaching negative infinity. How the heck did you do that? Well, I thought a little abstractly about this. And if I'm getting really, really close to 2 on the right side of 2, well, that means I'm a little bit bigger than 2. So if I looked at something over here, I have 5 over some number minus 2. It's a little bit bigger than 2, which means I'm going to have 5 over a very small number, okay? What happens to a fraction as the bottom gets smaller and smaller and smaller? Oh, the y value gets bigger and bigger and bigger. So I go up top. Well, if I'm looking from the left side, okay, now I have 5 over something minus 2. Well, if I'm on the left side of 2, maybe I'm at 1.9999999, and if I take 1.999999 minus 2, what I get is I get 5 over a very small but negative number. And the closer and closer I get to 2 from the left, the smaller and smaller that number gets. So when I have a fraction, I take a number dividing by something that's getting smaller and smaller and smaller, that's actually getting bigger and bigger and bigger. And when it's a positive number over a negative number, it's going to negative ginormous, which is really kind of negative infinity. So limits really allow us to analyze graphs, okay? And then no, that's not all they do. They do a lot more than just that. Limits allow calculus to work. Okay, well, what the heck are you talking about? There's all kinds of limits. I'm just going to look at a couple applications today. But let's say the question came out and I said, oh, well, I got this wonderful little curve. And, does anybody have a formula to find the area underneath that curve? No, they're going to say, I don't. Well, what if I knew and I calculated the area was 17? Okay, well, how did I do that? Well, I used a limit. I found so many, I just kept coming in here, and in integral calculus, this is what we'll do towards the end of the year. I'm going to build tons of rectangles in here, okay? And I'm going to find the area of all these rectangles. Well, I'm going to limit the number of my rectangles. Get abstract with me. I'm going to limit those rectangles to an infinite number of rectangles, and it's going to give me the perfect area underneath that curve, okay? Well, how the heck everybody always says, oh, I know how to find the slope of a line. That's pretty simple. Slope of a line is simply from point to point, it's rise over run, okay? And you've been told your whole life, you can only find the slope of a line. Well, let's say I have, that's a really crappy graph, but let's say I have a curve. Let's say, how the heck am I going to find the slope of this curve? Because yes, curves do have slope, okay? Just because it's not a line doesn't mean it doesn't have a slope. Curves have slope, and because that curve changes all the time, the slope changes everywhere on that curve. Well, how the heck would I find the slope of a curve at a point? Well, what I do is I keep coming in here and I keep picking points that are closer and closer and closer to that point. And what I do is I limit the change in x. As the change in x here, as my x interval gets smaller and smaller, as I limit that change in x to 0, what happens is those points become so super crazy close together that I'm able to find the slope of a curve at a point. That's the concept of a limit, is you're limiting something to get smaller and smaller, or in integral calculus up here, bigger and bigger, okay? And that's the concept of a limit. Now the top of the thing it says, and you don't have to draw these little chicken scratches I got all over here. It says limits and continuity. What the heck is continuity? Well, continuity, in calculus, we only like to work with functions that are continuous functions, meaning they don't have any breaks, jumps, or breaks and jumps. I'm going to leave it at that right now, okay? Because we need continuous functions when we're talking about a particular spot for a function. That function has to be continuous for us, otherwise the calculus doesn't work. We don't like to work with functions that have breaks in them, like piecewise functions. Think back to Algebra 1. Pre-calc, you did that. But we're talking about limits first today, because we cannot describe continuity without knowing what a limit is, okay? Limits help us describe whether a function is continuous or not, okay? So here we're going to kind of jump in here a little bit. Sorry for rambling and going. Limits, 2.1a, this is just an introduction of limits. Looking at this, what we will be talking about here, it's simply a very specific application of a limit. But we've done them already. You did them in Algebra 2 already. Okay, we've done them this year already when I went through and I did the door problem as a lesson. The door problem is a limit. Okay, and then you went in and you did the diving board problem as an assignment. It is an application, although both of these are a very specific application of a limit. You've done them, okay? And how is a door problem? How is a diving board problem? How is it a specific application of a limit? It is turning our A rock into an I rock, okay? It's limiting, it's making that time interval so itty bitty small that the lapse in time is so short, we can predict something at an instantaneous moment in time, okay? So I'm going to try to come along here. As we saw in the diving board problem and the falling ball problem, we can calculate average speed, okay? The diving board problem was the average speed coming down. The door problem was the average velocity or speed. We talked more velocity at the time with the door problem, where we took the change in degrees over the change in time, okay? And we can calculate the average speed, and speed equals the absolute value of velocity by computing the average speed, which is simply change in distance, change in time. Now, before I gloss over the top of speed equals the absolute value of velocity, okay, it's really important to understand speed and velocity have the exact same units: miles per hour, feet per second, gallons per minute. Speed and velocity have the exact same units. What differs speed from velocity is speed always carries a positive sign, because we're looking at your speedometer, okay? If you're going 50 miles an hour, you're going 50 miles per hour. Velocity carries the direction in which something is traveling. Velocity can carry either a positive or a negative sign. So if I said I was driving my car negative 30 miles per hour, well, that means I'm going in reverse. I'm going backwards. The negative denotes the direction I'm going. So when I'm looking at vertical motion objects, if my velocity is positive, I'm going up. If my velocity is negative, I'm going down, just like in the diving board problem. You could see when the guy was going up or down via the sign that the velocity had. Okay, we're just going to look at average speed here quick. Well, you can get kind of crafty. Math likes to call this delta D over delta T because the delta just stands really for change, okay? And we are going to apply this little specific example here. So, an object falls. I think I'm just going to get rid of this whole screen shade on here now, and we're going to look at this. An object dropped from rest from the top of a tall building falls F of t equals 16t squared feet in the first t seconds, okay? Really important to say because they're saying it falls 16t feet in the first t seconds. This equation is giving me the position of the ball. Okay, it's a position function. And when I'm thinking about average speed, we can do this all the time, okay? What I can do is I can find the position of the ball, and I can do that lots of different ways. Well, just think about this. Let's see what's happening to the position of the ball as time progresses. Well, if I found the position of the ball at time 0, it's at 0 feet, correct? What is the position of the ball 1 second after it's been dropped? Well, plug 1 into the equation and I get 16 feet. Well, that means here's my original position. 1 second in, it's fallen 16 feet. Well, what's the ball's position 2 seconds into its fall? Well, 2 squared is 4. 4 times 16, that would be 64 feet. Now, it doesn't mean that it fell 64 feet from second 1 to second 2, okay? Obviously, we can see here the change in distance from second 1 to second 2 is 48 feet. It fell another 48 feet to get to 60, but its position is 60 to get to 64, but its position is 64 feet away from where it was 2 seconds ago. If I look at f of 3, well, that's 3 seconds in. 3 squared is 9. 9 times 16, I believe that's 144 feet. So that means it came down here. Now its position from top to bottom is 144 feet, but it actually fell another 80 feet. It's this, my little line is not drawn to scale there, so it fell another 80 feet. Well, if we're looking for the average speed over the first 2 seconds, this is really kind of an elementary Algebra 1 topic to think about it, okay? To find the average speed you did, okay, aren't you just taking the change in distance divided by the change in time? And when I'm thinking about the average speed over the first 2 seconds, I don't need any big fancy formula for this right now. I knew I went from 0 to 64 feet, and it was over an interval of 2 seconds. That means my average velocity was 32 feet per second. Okay, that was I'm not going to say velocity, I should say speed, because that's what I'm calculating right here is speed. Okay, we could use a fancy formula for that. What is this 32 feet per second? Well, basically, it's what we did in Algebra 2. You would have done in pre-calc for a while last year, but you didn't. All it is it's the AROC, the average rate of change over the interval from 0 to 2 seconds. That's the average rate of speed the ball traveled, okay? It is still the same of the old f of b minus f of a over b minus a, okay? The 0 is my a value. The 2 is my b value, where we plug 2 into the function, okay? So f of 2 was 64 feet minus f of 0, which would have been my a value. So I had 64 minus 0. That's where my 64 feet came from. And then I took b minus a. I took 2 minus 0, and I got 2. I didn't really have to plug it into that big fancy formula right now because I had a wonderful table of values here that I could just say, hey, I went 64 feet in 2 seconds. Average speed was 32 feet per second, okay? Also, when I'm looking here, this 48 feet, on average, that ball fell 48 feet per second from here to here. Obviously, you can see from where the ball was dropped to where it was going down, each second it's covering a larger distance, therefore the ball is accelerating on the way down. It is technically traveling at a different speed every moment in time because it's accelerating, okay? And to find the instantaneous speed of the object at exactly 2 seconds in, what we're going to do is we're going to do the same thing we did with the door problem, the same thing we did with the diving board problem, is we're going to use an interval that's going to help us estimate the value, okay? And it's just kind of ironic the way this estimate comes out in this particular problem. Don't, read into anything. But if you're thinking about, oh, what the heck did we do? What do you mean we chose an interval that would help us estimate? Because we want that time to get so close. What we are doing is we're getting almost like from 2 seconds to 2 seconds. That's how we find an instantaneous speed. But if we did that, our change in distance and our change in time from 2 seconds to 2 seconds would be 0 over 0. It's going to give us undefined. So if we were looking at some intervals, okay, how did we do this? We said, oh, let's look from 2 maybe to 2.001. We use that interval. These are intervals of time. Another interval some people might use, maybe they're going to say, oh, maybe it's from 1.999 up to 2 seconds. Okay, that perfectly appropriate interval. Or there's another one that we could do. We could actually say, how about 1.999 to 2.001? Okay, I could go equidistant on both sides of my time 2 to find out what it is at 2. Okay, it doesn't matter which side of 2 you're on. It doesn't matter which one of these intervals I pick. The last one's kind of cool. But it doesn't matter which interval we pick, it's going to help us estimate. And how we did it in the door problem is we said, okay, say we picked this top interval. Well, we went from 2 to 2.1, and then we compared that to 2 to 2.01, and then we went to 2.001, and we kept going. We kept making this time interval between here get smaller and smaller and smaller. We were letting that time approach 0, okay? So what we are going to do is hopefully grab your calculators, and I know I showed you how to do this. We're not going to graph this. We're not going to do this from the graph. We're going to do this straight on our calculator. So grab your calculator. I showed this on a different one before. Somebody's texting me. Hopefully it shuts off pretty quick. I'm going to grab my calculator page, and what we want to do is we want to hit menu. We want to hit actions, and we want to, number 1, we want to define our function. We're going to define our function for the calculator, so it's going to do all these calculations for us. Now, when I'm in define, all I'm going to do is I can type in the equation, the function, however I want, but it has to be in function form, meaning I'm going to say f of t equals 16 t, I got to go t, squared. Okay, now you know when you're actually graphing, if you have a function in terms of t on your graphing page, you obviously have to put that in terms of x. When you're defining your function, you can define your function however you want, okay? However, it is very important that if you pick t as your variable is t on the other side. We have to have variable harmony in our calculator or it freaks it out and it will not do it. So after you type in your function, you just hit enter. It says done. I have now defined your calculator or defined your function. So if I need to evaluate this function at any point, let's see if I evaluated these correct. I'm going to say f of 0. Yep, it was 0. How about f of 1 second? We said it was 16. Yep. And I can say f of 2, 64. F of 3. Did I do that right at 104? And I did, okay? So now what we're going to do is we're going to use our calculator, okay? And I'm just going to zip this off a second. And we're going to use our intervals here. We're going to use our interval, and it doesn't matter which interval you pick, ladies and gentlemen, you have to understand this. We're going to use these intervals with our calculator, and we're going to go into, when we type it into our calculator, we're going to use this AROC formula when we plug it in there. So now I'm just going to come back to my calculator, and I like the old control divide function to get the fraction bar. And what I want to do is I'll do, I forget what the heck was it. Let me grab this. 2 to 2.01. So all I'm going to do is I'm going to type it into my calculator. It's important it's function form. F of 2.001 minus F of 2. And then, and then we're going to divide that by, if you want to do the mental math, you can. I'm going to just say 2.001 minus 2. And that's going to give us 64.01 feet per second is our estimate on that. Now watch, it doesn't matter which interval we use, like I said. So if I came up and I grabbed that, and I came from 2 to 1.999, and on the bottom I switch that out to 2 minus 1.999, 63.98. They're pretty stinking close. If I went equidistant on both sides of my interval, I'm actually going 2.001 to 1.999 over 2.001 to 1.999, and I'm assuming, based off of those first two estimates, you would have guesstimated roughly that you are going to be at about 64 feet per second, okay? Now, it's important to understand what we're doing here. These are approximated speeds. They're approximated, but what we did with our AROC formula is we got that interval of time so small that we are very confident that we can estimate the instantaneous rate of change, or the IROC, okay? And that's all we've really done there. So I'm going to turn my calculator down here, and I'm going to go to the next page. So we're just approximating that interval. I'd say recall from pre-cal, but you don't recall from pre-cal because you didn't do it last year. We would use an interval of 2, 2 plus h. Well, don't get confused by this plus h, okay? Like if I was looking at my first interval, I'm saying h equals 0.001, and that's giving me my interval of 2, 2.001. That's where my interval is coming from. H, and I'm allowing h to change, okay? It's just one of the mathematical things we do here in calculus that you would have gotten there. And then as we pick values, as we pick numbers for h, we let h go to 0. And what happens is, when we let h go to 0, we end up finding the instantaneous rate of change, okay? So, we're going to let h equal 0. Above, we're still using the same function, f of t equals 16t squared, okay? Now, AROC, over here. Don't get all confused. What is this 2 plus h? What is all this? Well, we're finding the average rate of change over that interval. We are still using f of b, minus f of a over b minus a, okay? Because all I'm doing is I'm taking this function and I'm letting, here's my interval for b, here's my interval for a. So this gets plugged in. So how do I do that? Well, if I'm plugging 2 plus h into my function, well, I get f of 2 plus h minus f of a, well, that's plugging the 2 in over b minus a, okay? So we're going to cruise along through here with that. And if you would have done this last year, which you didn't, well, what happens is that actually gets plugged into your function. I'm not going to spend an over great deal of abundance of time, but if I put 2 plus h, when I taught these difference, it's the difference quotient actually. I always had students start out with brackets because there's a major sign drop, many students do, and they always forget to distribute this sign at the end. So I always say put out some brackets, and then what we're doing is we're taking 16, and anywhere we see that t value, we are plugging in our 2 plus h, because that's my f of b right here. And when I plug it in, then I get minus f of 2. Well, that's grabbing my 16 and just putting 2 in for t. And then on the bottom, I have b minus a, which is my 2 plus h minus 2. Well, and then I start my algebra. Well, in the end, remember, this is 2 plus h times 2 plus h right here. It's not 4 plus h squared. So we're going to end up having, when I do this, I have 16 times, well, when I take 2 plus h times 2 plus h, I actually get 4 plus 4h plus h squared. If you don't trust me, lay it out and FOIL it, minus 16 times 4. And then if I collected some like terms down here, I could see 2 plus h minus 2. I just get over h, and that's what's going to happen every time. Now if I continue on, now I got to distribute that 16, and I get, what do I get? 16 times 4, that gives me 64 plus 64h plus 16h squared minus 16 times 4 is 64, and that's all over h. I collect my like terms on the top, and I'm like, whoa, that's kind of crafty. That's pretty nice. Those 64s just canceled out. So what I do is I see here in the end, oh, there's a common factor of h left in there. Let me factor that little h out of there. Huge point, 64 plus 16h, and this is all over h. I'm like, whoa, check this out. I can reduce my h. Well, that means the AROC from 2 to 2 plus h over the interval, that's a crappy h, equals 64 plus 16h. Well, what's that used for? Well, this is a really nice little equation that I can use, and as I plug in values for h, okay, what I'm doing is I can make that time interval bigger or smaller, okay? Well, what the heck are you talking about, Kruger? Well, now you can see that there. So what I'm going to do, come over here, I'm going to say, okay, so let me draw a line here. Let me say, what happens if h equaled 3? Well, if h equaled 3, I'm looking for the AROC from time interval 2 to 5. Because see, there's my h. So I'm going from 2 to 5. Well, what is that? Well, I can find that really quick by saying 64 plus 16 times 3, and I'll plug that 3 because this is a function that's going to give me my average rate of change around 2 only, because it's 2, only 2, and I'm going to see that that is, oh, that's about 112 feet per second. Well, what happens if h equals 2? Well, now that's the AROC from 2 to 4. That's going to give me 64 plus 16 times 2, which is, what does that give me? 96 feet per second. And then I could say, oh, what if h equaled 1? Well, that is my AROC from 2 to 3. Notice all I'm doing is I'm plugging that h in here to find a new time interval. And that's going to go to 64 plus 16 times 1, technically. And that's going to give me 80 feet per second. Well, what happens if h equals 0.1? Well, that's narrowing down. So you can see I'm making my time interval smaller and smaller. So that's my AROC, and I'm just going to put an A2 to 2.1. Well, that's 64 plus 16 times 0.1. Well, that's 64 plus 1.6. That's 65 60.6 feet per second, excuse me. Okay, and if I continued on this journey, let's say h is now 0.01. Well, that's giving me my AROC of 2 to 2.01. Notice I'm getting this time interval closer and closer to what our approximation was before, but I'm pushing it through a specific function that we built with the AROC, allowing one side of 2 to change. And this is going to give me 64 plus 16 times 0.01. Well, that's going to give me, what does that give me? 64.16 feet per second. Okay, and as I allow, it's the whole concept of a limit here, folks. It's the whole concept of a limit. As h approaches 0, what happens is we get the limit as h approaches 0 of this function, 64 plus 16h, equaling 64 feet per second. Okay? And what it actually represents in this form, as h gets super close to 0, that whole section goes away, it gets 64 feet per second. What that actually represents is that represents the rate at exactly t equals 2 seconds. Don't read into the 64 feet per second with the 64 feet of drop, okay? Well, Mr. Kruger, what happens if I want to know what the instantaneous rate of change is at 3? This is not the right function for it anymore, okay? If that were the case, I would have to find the AROC, and you would have done this time and time again in pre-calc last year, from 3 to 3 plus h, and I would go all the way through that f of b minus f of a over b minus a, which would have turned into, remember, f of x is 16t squared, f of t, variable harmony. Well, what is f of b? That gives me f of 3 plus h minus f of 3 over 3 plus h minus 3. And then I'd have to start in there again, and then I'd have brackets minus brackets over, and then I have 16. I'm plugging my 3 plus h in, and I got to square that. And then over here I have 16 times 3 squared. And here I have my 3 plus h minus 3. Those are always going to cancel out. And that's going to give me, and I'm going to stop here, but it's 16 times 9 plus 6h plus h squared, because I took 3 plus h times 3 plus h, minus 16 times 9. Did a little math down here, it's over h, and I would have kept distributing, but hopefully you can see all these numbers here changed, that changed. It's going to be a completely different function than we got back up here. Where is that dirty little rascal? Right here. And then we let h change and we narrow up our look at it, or our interval on it, if I can say. Look isn't really the right word for it. So hopefully that's making a little bit of sense as we're coming along with our concept of a limit here. And as you turn your page here, actually you're still on the same page, this is the mathematical concept of a limit. By taking a limit as h approaches 0 over an average rate of change over an interval of 2 to 2 plus h. Now this interval can be anything. This is finding, because it's 2 to 2 plus h, we could actually calculate the instantaneous rate of change at t equals 3. If I wanted to know the instantaneous rate of change at t equals 4, my interval would change to 4 comma 4 plus h. and this denotes how I can see what my interval's at, okay? And the notation is down here. We found this little function, okay? Now, it's important to understand this is a specific situation of applying a limit. There's lots of applications of limits. This is only one of them, okay? And what it represents up here, the notation, the limit as h approaches 0 of 64 plus 16h equals 64. What this communicates to us is, because I'm applying a limit, because this time interval right here, I'm letting that time interval go to 0, this goes away, and I'm at 64 feet per second. It actually represents the instantaneous rate of change at t equals 2 for this function only, 16t squared. It is 64 feet per second, okay? And a working definition of the limit, I think you guys are getting close to the bottom of your page here. Working definition of the limit, okay, for f of x, what it means is as the inputs x get closer and closer to some specific value c, okay, this specific value c is an x value, okay, so as gets closer to a specific value c, and the outputs y get closer and closer to a specific value L, that's a y value, then we can say, okay, how this is math. We just need to learn to talk the new math language. The limit as x approaches c of f of x equals L. Or you can also be read as the limit of f as x approaches c equals L. Okay, f of x, what it means is my whole function is approaching an ordered pair right here, c comma L. Okay, it's approaching this ordered pair of c comma L. It is pretty important to understand that the function does not have to physically touch L. It just needs to approach it, okay? So to think about this a little bit, the answer to a limit is always unconditionally going to be the y value of a potential ordered pair. The limit value, it's just another way to state it, the limit value is the y value. Okay, what do limits do for us? Limits give us a language for describing how the outputs of a function behave as the inputs approach a specific value or approach infinity. Okay, this is, okay, a limit is the fundamental concept of which all calculus is built. There's 5, 6 calculus classes. They all rely on the concept of a limit, okay? It gives us a language, right? That beautiful language down there. Why do I need to know limits? Well, think all the way back when you first started math. You didn't know anything existed with negative numbers, and then you were introduced to negative numbers, and a whole new world of math opened up to you. Well, a whole new world of math is starting to open up to you with the concept and understanding of a limit, okay? It's a language of abstract thought. Okay, I'm going to back this up one thing yet because I want to make sure everybody is very, very clear here, okay? F of x, my function, might not actually pass through this point of c comma L. This is the understanding of a limit, okay? But it doesn't have to actually touch that point for the limit to exist. And that sounds really abstract. It's going to come together here. And what we're going to do here is we are going to explore f of x equals x squared minus x, or excuse me, x minus 2 over x squared minus 4. I do not want you to graph it yet, okay? Please don't graph it yet. Let's just look at this little bugger once for a second, okay? There's things you really need to start to just jump out and grab you. and things to refresh your memory. Hold on. Uh-oh, I'm still recording. Hold on, Emily. Do not graph this yet. There are certain things that I kind of expect you know when you're looking at this. First and foremost would be the domain, that you would be able to tell me the domain is all real numbers x except -2 or 2. Well, how the heck do you know that, Mr. Kruger? Well, I know this is a rational function, and I know the denominator, I'm a factorer, not a solver, that this is x plus 2 times x minus 2, so I can rename that. So that -2 and +2 both give me zeros in the denominator, therefore I'm undefined twice in this function, so I would have to be there. Well, limits help us investigate what's going on at these points. For instance, let's investigate what's going on at f of -2. Well, all I'm going to do is I'm going to plug -2 in there into my function. Okay, so I have x minus 2 over x squared minus 4. Well, what does that give me? If I put -2 in there, I get -4 over 0. And what does -4 over 0 mean? It means undefined. Undefined how? Vertical asymptote. That is right. We have a vertical asymptote at x equals -2, because you're thinking back to your pre-calc days, you're thinking back to your Algebra 2 extended days, and you remember that anytime you have a number divided by 0 equaled vertical asymptote. Okay? Well, let's investigate. So what's going on at f of 2? Well, if I plug 2 in there, what happens is I get 0 over 0. Well, what happens when I get 0 over 0? Whoa, think back, think back. Ooh, that means we had a hole in the graph. We had a hole at x equals 2, so we had a hole at 2 comma something. And we even taught you how to find that hole, okay? And when I think about it, how did we find that hole? Well, the only way that this 0 over 0 happens is the top and the bottom, the numerator and the denominator, both share the same factor to make the top and bottom 0 at the same time. Oh, I kind of remember that, Mr. Kruger. So check it out. Common factor, common factor. This thing would simplify to 1 over x plus 2, and then we'd put the 2 into our simplified, and we got a fourth. Oh, ooh, we had a hole at 2 comma 1/4. Okay, maybe that remembers or not. Last thing we're going to talk about, a horizontal asymptote. Aha! Where do I have a horizontal asymptote on this little bugger? Yeah, y equals 0. How did you know it was at y equals 0 so fast? Because I kind of came back and I kind of looked here and I compared my powers. Bigger in the bottom is always y equals 2. Okay, so all we're going to do is we're going to take that large power in the bottom, y equals 2. Larger power in the top, doesn't have one. Same powers, lead coefficient over lead coefficient. So what do we do from there? People got to quit texting me. What I want to do, now let's enter that into our graph. Let's enter that little function into our graph. I'm going to add myself a page here. I'm going to add a graph. I'm going to give it the old control divide. And in the numerator, I'm going to say x minus 2. And in the denominator, I'm going to say x squared minus 4. I'm going to enter it in graph. Okay? And we're going to look at these problem areas. Well, once it's graphed here, let's see. I only see one vertical asymptote, but I have 2 undefined spots. Well, we're going to go here, menu, trace graph, and we're going to look at -2. 2, -2, undefined. It even shows me that vertical asymptote. That dashed line means I'm undefined at that point, but I can kind of see my graph crawling up and down both sides of that. Okay, well, how about at +2? Well, I don't have a vertical asymptote there, but if you kind of take a little look down here, that ordered pair is still undefined. But my graph doesn't show me a hole in the graph. How the heck? When I evaluated my function, I said it was a quarter. Well, that's the whole concept of a limit. Let's check it out. Let's get a little bit on the right side of 2, like maybe 2.001. Ooh, there's the quarter. How about the left side of 1? Maybe 1.999. Ah, there's my quarter again. I'm a little higher because my function's decreasing there. So I can see the limit, that value 2, 1/4, that point does not exist on the graph, but the limit exists, okay? So we can look through all that stuff. My horizontal asymptotes, I can see when I look out to the edge. So how are we going to be investigating all of these functions, okay? Well, you can fill these in. You'll need to be able to find the limit of any function as x approaches different values using the following 3 methods, okay? We will find them algebraically, and that is through simplification and or substitution. Graphically, just like I did on the calculator there, and I used the trace feature and I got close to it, or numerically, where we will use a table of values on the calculator. We don't want to make all these terrible decimal calculations, so we're going to let the calculator make that for us. We won't do it numerically a lot, but we will do it algebraically and graphically a lot. And you don't always need your calculator to investigate something graphically. Lots of times there will be lots of instances in which you are given a graph to where you need to graphically identify the limit if it exists, because you won't have a function to algebraically manipulate. Yay! Let's go check out 1. I think I'm just going to do this 1 yet, and then I'm going to shut her down, and we're going to finish this up tomorrow and do the next lesson, and then you guys will be ready for your homework in chapter 2 or section 2.1. Okay? Algebraically. So how do I algebraically find a limit? Well, super easy. It's called substitution. What do you mean, substitution? Plug it in, Glade air freshen that little bugger. So the limit as x approaches 0 of x minus 2 over x squared minus 4 equals, now check it out, I got a whole brand new target place. Before I looked at -2 and 2, now I'm looking at a super duper boring spot, 0. So because I'm approaching 0, I'm going to look at this, it's -2 over -4. Oh, my limit's a half. Yay. It's not too hard. I can see that on my graph, because if I typed in a 0, check it out, it even goes through that point, and my limit is right there. Okay, that's algebraically doing this. Okay, graphically. Well, graphically, guys, it's pretty important. I'm going to try to get myself a little bit more room here. Graphically, it's really important to be looking at it in 2 ways, okay? I want to look at the limit as x approaches 0 of, is it okay if I just call this f of x, because I don't want to write everything down? I will, I'll write it. X minus 2 over x squared minus 4, okay? It's super important that we look at this on both sides, because I have this side and I have this side. I have a right side and I have a left side of 0, okay? And it's super important because looking right here, it's implying two-sided. We'll get to one-sided limits soon enough, but that means I am looking here at what the heck is the limit as x approaches 0 from a little bit bigger than 0, that's what that plus sign means, or the right side of that function, x minus 2, x squared minus 4, okay? And if I was doing that graphically, this would look like x 0 from the left, x minus 2, x squared minus 4, okay? And all we're going to do is we're going to go back to our graph. And like I said, it's really important that if I'm on the right side of 0, I'm just a skosh bigger than 0. So I'm going to say like maybe 0.001. And looks like 0.49, 0.000001. Get even closer. 0.5-ish. Okay. And then if I went under 0, I'm at 0.999. Ooh, no, I'm not. I'm negative 0.001. And I can see I'm approaching a half there. And in this case, even when I hit 0, this point exists on the graph. It's really a boring point. However, graphically, it is very, very important that you do investigate both sides, okay? You have to investigate both sides. And if I looked at this right, if I would have written this down, this side was, I got like 0.499 something. This side, say it was 0.5, depending how close we got. So right in the middle, I can see both the right side and the left side are coming together at 0.5 or 1/2, okay? Numerically, again, we'll do the numerical aspect of this with our calculator. And as soon as I get this one done, I'm going to quit this video. But numerically, what we're going to do is we're going to pull up our calculator, and I'm going to exit out of my tracing. And I'm going to say menu. And I got to remember I want to view, I got to remember, table. I want to split my screen. So split screen table. And this right here, these are only going up by increments of 1. So when I hit menu again now, and I hit table, I want to look at my table settings to do this tabularly. And I want the independent variable to be on ask. It's going to let me put anything in I want for x and hit OK. Now I can put in any x value I want. So if I'm here, and let's say I was at 0.1, and then I go to 0.01, 0.001, I can get closer and closer to 0 from the right side. And if I went now if I went to the left, equidistant, I was like negative 0.001, negative 0.01, and negative 0.1, I can really kind of see in my graph that as I get closer to 0 this way, and as I get closer to 0 from the negatives, they are basically converging on the point 1/2. Okay, we won't do a lot with the tables. Tables are, we will do a little bit, but not a lot. And actions, I don't want to resize, remove table. I can see my graph normally, but that's how I would see it in my table. It's really important to see in this point, or this problem, that f of x approaches the point 0, 1/2. That point exists this time, okay? Like when I was up here doing the algebraically one and I plugged it in, you're like, dang, limits are easy, I love these things. Well, give it a little time. Not too much time, but give it a little bit of time, it'll come back. So this video is already longer than I wanted to make it, so I'm going to cut the rest of this into tomorrow's video to start out the rest of this packet, and then we'll move into the next one. No homework tonight. Have a good day.